What if we find water on the moon? If we find water on the moon, it would have significant implications for future space exploration. Water is a valuable resource in space, and it can be used for a variety of purposes such as air, water, and propellant. If we can extract water from the moon, it would make it easier and more cost-effective to establish a permanent human presence on the moon and beyond. So finding water on the moon would be a significant discovery with far-reaching implications for space exploration. It would make it easier to establish a permanent human presence on the moon and beyond and could lead to new discoveries about our solar system's history. How can water be used as propellant in space? Water can be used as propellant in space by splitting it into hydrogen and oxygen gases and burning them in a rocket nozzle to generate thrust. According to NASA's Pathfinder Technology Demonstrator 1, a new type of propulsion system that uses water as fuel. The system will carry a pint of liquid water as fuel and split the water into hydrogen and oxygen in space to burn them in a tiny rocket engine for thrust. Water is a valuable resource in space, and it can be used for a variety of purposes such as air, water, and propellant. Traditional high-performance fuels pose risks, including toxicity, flammability, and volatility. The use of such rocket fuels for in-space propulsion systems requires extensive safety measures, which drives up mission cost. To make these propulsion systems feasible for CubeSats, good propulsive performance needs to be balanced by safety. In addition to this, if plentifully available in CIS lunar space, water could be used directly as propellant in solar thermal rockets, STRs, to provide inexpensive transportation. Why solar thermal rockets not used yet? Solar thermal rockets are still in the experimental stage and have not yet been used for space missions. One of the main challenges with solar thermal rockets is that they require a large surface area to collect solar energy, which can be difficult to achieve in space. Additionally, the high temperatures required to heat the propellant can cause damage to the rocket's engine and other components. Another challenge is that solar thermal rockets are not as efficient as other types of propulsion systems, such as chemical rockets, which use high-energy fuels like hydrogen and oxygen. However, researchers are working on developing new materials and designs that could make solar thermal rockets more efficient and practical for space travel. In conclusion, while solar thermal rockets have the potential to revolutionize space travel, there are still many technical challenges that need to be overcome before they can be used for space missions. Chandrayaan-3 latest findings. The Indian Space Research Organization, ISRO, has shared the first findings of the Chandrayaan-3 mission. The payload on the Vikram lander has measured the temperature of the moon's soil, which increases as depth increases. The payload has a temperature probe equipped with a controlled penetration mechanism capable of reaching a depth of 10 centimeters beneath the surface. The Chandrayaan-3 mission aims to demonstrate India's soft landing capability on the moon. The lander and rover will communicate with Earth via an orbiter from Chandrayaan-2. The rover, named Pragyan, is equipped with two key features, the alpha particle X-ray spectrometer and a laser-induced breakdown spectroscopy, both of which are capable of determining the chemical elements present in soil and rocks on the lunar surface. How the alpha particle X-ray spectrometer, APXS, works. The alpha particle X-ray spectrometer, APXS, is a device that analyzes the chemical composition of a sample by measuring the scattering of alpha particles and fluorescent X-rays after the sample is irradiated with alpha particles and X-rays from radioactive sources. This method is often used in space missions because it requires low weight, small size, and minimal power consumption. The APXS carries a small alpha particle source, which emits alpha particles during radioactive decay. When these alpha particles collide with the atomic nuclei of the sample, some of them are backscattered to the detector. The energy distribution of the backscattered alpha particles can be analyzed to determine the elemental composition of the sample, especially for lighter elements. Additionally, some of the alpha particles are absorbed by the atomic nuclei, producing protons that can also be detected. The APXS also uses X-rays to analyze the sample. When the sample is irradiated with X-rays, it produces fluorescent X-rays that are characteristic of the elements present in the sample. The energy distribution of these fluorescent X-rays can also be analyzed to determine the elemental composition of the sample. Overall, the APXS provides valuable information about the elemental composition of rocks and soils, which can help scientists understand crustal formation, weathering processes, and water activity on other planets. How the laser-induced breakdown spectroscopy works. Laser-induced breakdown spectroscopy, LIBS, is a type of atomic emission spectroscopy that uses a highly energetic laser pulse as the excitation source. The laser is focused to form a plasma, which atomizes and excites samples. The formation of the plasma only begins when the focused laser achieves a certain threshold for optical breakdown, which generally depends on the environment and the target material. When the laser pulse is focused on the sample's surface, it ablates a tiny fraction of it into a plasma, a particular state of matter characterized by high temperature and strong ionization. The optical radiation emitted by the hot plasma is then collected and spectrally decomposed to obtain information about the composition of the sample. LIBS can be applied to the study of solids, liquids, and even gases. Overall, LIBS provides valuable information about the elemental composition of materials, which can help scientists understand their chemical makeup. It has been proposed and tested in practically every field of application of analytical chemistry, for industrial and environmental diagnostics, forensic analysis, biomedicine, cultural heritage studies, and many other fields.